Today we have this double integral from the Romanian Mathematical Magazine, and this integral was designed by Ankush Kumar Parcha. Now, Ankush has this really interesting habit of designing double integrals with special attention to symmetry, and this integral is no exception. It actually has a very beautiful symmetry to it that's going to be very helpful for our solution development. Let me show you what I'm talking about. First up, we're going to make use of the linearity of the double integral operator and write this as the double integral from 0 to pi by 2 of sine x divided by cosine x plus cosine y dx dy plus the double integral from 0 to pi by 2 of sine y divided by cosine x plus cosine y dx dy. Now, let's turn our attention to the second double integral, and why is this so annoying today? Much better? Anyway, so let's turn our attention to the second double integral here, and notice that because we have a bounded function of both x and y, which we're integrating over a bounded region, the integral converges. And because it converges, there's no harm in switching up the order of the integration operators. So we might as well write it as the double integral from 0 to pi by 2 of sine y divided by cosine x plus cosine y dy dx. Now, because x and y are just dummy variables, we can butcher their names however we like. So why not just switch them up? So we have x and y being interchanged, and that means we now have the double integral from 0 to pi by 2 of sine x divided by cosine x plus cosine y dx dy, which is exactly the integral we have here. So all of our hard work implies that the target integral I equals twice the double integral from 0 to pi by 2 of sine x divided by cosine x plus cosine y dx dy. Now, the first integration is being carried out with respect to x, meaning that y is being held as a constant. So the function in the denominator has its derivative up in the numerator. So that means, well, the negative of the derivative anyway. So that means we have I being equal to negative 2 integral 0 to pi by 2 logarithm cosine x plus cosine y, with the limits being 0 and pi by 2, dy, which sorts out to negative 2 integral 0 to pi by 2. And we have the logarithm of, let's see, as x approaches pi by 2, we have cosine of x approaching 0, so that leaves cosine y minus the logarithm of as x approaches 0, we have cosine approaching 1, so that's 1 plus the cosine of y dy, and we could get rid of this negative sign if we just flip the order of these two terms. So we have twice the integral from 0 to pi by 2 of log cosine y dy minus, no wait, I had to flip them over. So we have 1 plus cosine y dy minus twice the integral from 0 to pi by 2 of log cosine y, which is one of Euler's famous log-trig integrals, and this sorts out to negative pi by 2 times log 2. Multiplying that by 2 means that I equals, I'm going to call this integral here I sub 1. So we have 2 times I sub 1 minus, no wait, plus pi times the logarithm of 2. And now let's evaluate I sub 1. Now for the integral I sub 1, we're going to reference old reliable here. That is the double angle formula for the cosine function. We can write 1 plus cosine y as 2 times cosine square y by 2. And that implies that I sub 1 equals the integral from 0 to pi by 2 of log 2 cosine square y by 2 dy. And now using the properties of the logarithm, which we know and love, we can write this as the integral from 0 to pi by 2 of log 2 dy plus the integral from 0 to pi by 2 of log cosine square y by 2 which of course could be written as twice the logarithm, and in this case twice the integral. Okay, cool. So the first integral here is fairly simple. We get pi by 2 times log 2. I don't know why is it fairly simple instead of extremely simple, but was there ever a need to quantify how simple this integral is at this stage? I don't know. I'm overthinking it. Let's just move on. So we have this new integral, twice this new integral. And for this integral, I'm going to invoke a substitution. We're going to let y by 2 equal u, which implies that dy equals 2 du. So that means the new and improved integral is twice the integral from 0 to pi by 4. Let me just move this down a bit. Okay, so it's the integral from 0 to pi by 4 of, what exactly do we have? We now have log cosine u, and the differential element has this extra factor of 2, so that means we have 4 outside du. Okay, cool. And now for the new integral, we're going to reference one of my all-time favorite series expansions, the one for log cosine x. Link in the description below for a beautiful proof using complex analysis. So we have log cosine u equal to negative log 2 plus the sum over the positive integers k of negative 1 to the k plus 1 times cosine 2ku divided by k. And we're interested in the integral of log cosine u from 0 to 1/4 of pi. So that means for the first integral, we would have negative pi by 4 times log 2. And for the sum of integrals on the right, for the integral of the sum on the right-hand side, we can switch up the order of the summation and integration operators, once again because of convergence. We know that the integral on the left-hand side converges because it's the integral of a bound function over a bounded interval. And that means it converges, so whatever you have on the right-hand side converges as well. Okay, cool. So that means we have the sum over the positive integers k of negative 1 to the k plus 1 divided by k, where I just taken all the pure k terms outside the integration operator, and we now have the integral from 0 to pi by 4 of cosine 2ku. And this is a pretty simple integral to evaluate as well. We have negative pi by 4 times log 2 plus the sum over k of negative 1 to the k plus 1 divided by k times the sine of 2ku divided by 2k, with the limits being 0 and pi by 2. So that means we have negative pi by 4 log 2 plus the sum over k of negative 1 to the k plus 1 divided by 2k squared, and the sign of 0 is just 0, meaning that we're left with the sign of k times pi by 2. Now, the sign term here is pretty interesting. Whenever k is even, like 2 times n, where n is a positive integer, we have sine of n times pi, which is of course 0. But for k equal to 2n minus 1, we have sine of 2n minus 1 times pi by 2, which is of course equal to negative 1 to the n, right? So that's sorted out, and we have I sub 1 equal to negative pi by 4, and we have this factor of 1/2 as well. Wait, we had this factor of log 2. Now we have this factor of 1/2 times the sum over the positive integers n now of negative 1 to k is replaced by 2n minus 1. We have this plus 1. They cancel out quite nicely. Divided by k squared is now 2n minus 1 squared, and we have negative 1 to the n. So that means we have negative pi by 4, that is, times log 2 plus 1/2 of the sum over the positive integers n of negative 1 to the n divided by 2n minus 1 squared, which is, of course, Catalan's constant. So we have negative pi by 4 times log 2 plus 1/2 of Catalan's constant. That's I sub 1. Nope, wait, false alarm, that's not I sub 1. That's in fact the integral from 0 to pi by 4 of log cosine u du. And I sub 1 was something else. It definitely was related to this result. And wait, those are two equal signs. Much better. So I sub 1 was in fact pi by 2 times log 2 plus 4 times the integral above. So that means we have negative pi times log 2 plus 2 times Catalan's constant. And we have pi by 2 log 2 minus pi log 2. That's 1 minus, no wait, that's half minus 1. So you have negative pi by 2 times log 2, which was the hardest part of the solution development. Now that we have I sub 1, we can return to the target integral I. The target integral was what exactly? I do not remember. Wait. It was pi times log 2 plus twice the result of I sub 1. So that means we have negative pi log 2 plus 4 times Catalan's constant. So that's some lovely cancellation, and we conclude that the double integral, wait for it, from 0 to pi by 2 of sine x plus sine y divided by cosine x plus cosine y dx dy equals 4 times Catalan's constant. And I think this is just a beautiful double integral representation of Catalan's constant. I mean, it's wonderful. It's absolutely beautiful once you look at it this way. I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.